In April 1954, the Royal Aircraft Establishment was asked to conduct an exhaustive investigation to find possible reasons for recent accidents to Comet aircraft, which constituted a serious threat to our aeronautical progress. Accident investigations are a regular job with us, but this was perhaps the most important we have tackled. The first accident covered in this investigation occurred on the 10th of January 1954, shortly after takeoff from Rome, the aircraft falling into the sea near the island of Elba in the Mediterranean. The second accident occurred 3 months later, again shortly after takeoff from Rome, the aircraft falling into the sea near Naples. Immediately after the Elba accident, the Royal Navy salvage ship, Sea Salvage, assisted by other craft, began operations to recover the wreckage. A diver in an observation chamber was lowered into the sea and from a position near the seabed directed the salvage operations. During the difficult search for wreckage at a depth of over 400 feet, underwater television, in an improved form to that used for examining the lost submarine affray, was used to identify wreckage on the seabed. Piece by piece, the wreckage was picked up and brought to the surface by a giant salvage grab weighing nearly 5 tons, delicately controlled from the deck of the Sea Salvage. While salvage operations proceeded, the scientific resources of the establishment were mobilized, the director and senior staff planning the main lines of what is perhaps the most exhaustive accident investigation ever carried out on a single aircraft. As parts of the Elba Comet were recovered, they were immediately flown back to Farnborough, where the intricate job of identification and assembly began. It must be remembered that at the beginning of this difficult investigation, there were no clues to explain the cause of the accidents, neither was it known how much of the wreckage would be recovered. Broadly speaking, the problem resolved itself into 2 major lines of investigation. Firstly, examination of the wreckage, and secondly, detailed testing of Comet aircraft and equipment. A really formidable task when it is remembered that each Comet is made up from some million separate parts, any one of which might have contained a clue. Teams of scientists and technicians were set up to investigate every conceivable theory or equipment which could have contributed to the accidents, including such aspects as consideration of the strength of the aircraft's structure, the possibility of fire or explosive damage, and the aerodynamic aspects of aircraft behavior. The possibility of failure of the controls, including autopilot, hydraulic, electrical and radio equipments, had also to be considered, and these investigations were supplemented by flight tests with a BOSC Comet aircraft. The seemingly chaotic mass of wreckage from the Elba Comet was arriving at Farnborough, and the baffling work of identifying the pieces and searching for clues to the accident went on. In the end, the Navy was able to pick up 70% of the Elba Comet, a fine piece of salvage work. During all these intricate phases of the investigation, we kept an open mind regarding the probable causes of the accidents. The reason for the accidents was only finally accepted when it became clear that the evidence from all the sources fitted together and produced a coherent and consistent picture. In the following sequences of this film, technicians describe how the major stages of the investigation were carried out.
Amongst many possible lines of inquiry was the fatigued life of the aircraft structure. Fatigue is a tendency of metals to break under comparatively small loads, if these are repeated often enough. It was therefore decided to construct a new type of test rig, to see if there might be some unpredictable interaction within the cabin structure between the gust loads and the pressure loads. The site was cleared, and work started on a testing tank, in which a complete Comet could be fatigue tested. The civil engineering work consisted of 2 pressed steel tanks, each having a capacity of 218,000 gallons. The second tank, was used as a storage reservoir when it was necessary to empty the test tank for detailed inspection of the aircraft. Comet Uncle was stripped of its furnishings, engines and equipment, and delivered by road to Farnborough, where it was reassembled. This aircraft had already flown about the same amount as the Elba Comet, 3,500 hours. Failure of the cabin under air pressure would create a major explosion, as is shown by this test specimen pressurized to destruction by air. This sectional model shows how we solved the problem. The cabin was placed in a tank, and the tank and cabin were filled simultaneously with water. The water pressure in the cabin was then increased to simulate the differential pressure that occurs in normal flight. Upon arrival at Farnborough, the various sections of Comet Uncle were assembled. The aircraft was then wheeled into position in the partially completed test rig. This exacting operation required careful planning and good teamwork to make sure that the aircraft was accurately positioned in the tank. Since it was intended to simulate wing loadings due to normal flight loads and gust, as well as the pressure cabin loads, it was necessary for the wings to protrude through the sides of the tank, so that they could be subjected to a limited amount of movement. The tank was assembled from components similar to those used in the wartime static water tanks. This method of construction lent itself to rapid assembly. The metal box sections surrounding the wing apertures were fabricated in the establishment's workshops, and work on them proceeded at pressure, so they would be ready to include in the tank without holding up its construction. When completed, they were built into the tank to form the apertures through which the wings protruded. Each section weighed about 8 tons. Nice handling. It looked easy here, but a miscalculation might have seriously damaged the Comet wing. To keep the water in the tank, and yet allow the wings to move freely, seals of rubberized fabric were designed and made. The seals being shaped to follow the airfoil section of the Comet wing just outboard of the engines. A specimen of the seal was fastened to a specially constructed mock-up Comet wing section. The wing and seal were then given a laboratory test in a special water tank. The seal being subjected to the same movements and water pressure would have to sustain in the finished test rig. The test having proved successful, similar seals were then fitted to the Comet wing and the test rig. This important operation had to be done with great care to ensure that when the wings were moved to simulate flight loads, the seals would flex and yet support the weight of the water in the tank.
At night, work went on without a break. By the light of a battery of floodlights, the test rig continued to grow at a rapid pace under the skilled hands of technicians and craftsmen. Normally, the design and construction of such a complex testing rig would have taken 2 years. The fact that it was completed in 6 weeks is some indication of the magnitude of the effort made by all engaged on the project. Salute to the men and women who made this achievement possible. Machines did a lot of the work, but the deciding factor was the quality of the human beings behind them. The typical English summer did not help the work. We had more than our fair share of this sort of thing. But in spite of difficulties and discomforts, work went on at high pressure. Nothing could damp the determination of the men on the job to get the test rig working in the shortest possible time. Fortunately, the sun shone sometimes. The shirts came off, but the work went on. Only 6 weeks after design work began, the fatigue test tank was completed and ready for the test to begin. Bars of lead ballast were added to represent the all-up weight of the aircraft and passengers, the furnishings, etc. being removed before the test began.
Pressure cabins are tested using water because if air pressure were used, a major explosion would occur when the cabin failed. To identify the places where failure began, we must localize the damage as much as possible. Water testing enables us to do this. Final preparations were made for filling the tank. After weeks of intensive work, the tank is filled. And everything is ready for the tests to begin, including safety precautions for the over-enthusiastic. The tests undertaken simulated the average pressurized Comet flight of 2 3/4 hours in just over 5 minutes. Loads were applied to the wings and rear fuselage to represent the average effects of encountering up and down gusts of 10 feet per second in level flight. In the tests, the aircraft was originally loaded as if it was standing on the ground. Loads were then applied to represent the level flight conditions, and the gust loads were superimposed on these. The differential cabin pressure was at the same time increased from 0 to 8 1/4 pounds per square inch, as occurs in a climb to 40,000 feet, and then reduced to 0 again to simulate the descent. The number of gust loads applied in each simulated flight cycle was based on an analysis of accelerometer records made during 2,000 hours flying of comets on BOAC routes. At the end of the cycle, the loads represent the aircraft on the ground. Wing loads were applied by hydraulic jacks, 25 gust cycles and 1 pressure cabin cycle being imposed every 5 minutes to simulate a flight of approximately 2 3/4 hours. The rise and fall of pressure and application of gust cycles was made to correspond to operational conditions, with most of the gusts occurring at low altitude. A helicopter view shows the Comet fuselage submerged in the water tank, with the aircraft wings projecting through the tank on either side. Hydraulically operated mechanism applied simulated gust loads to the rear fuselage. From time to time the tank was drained, and the aircraft examined by technicians, wearing waterproof suits.
Meanwhile, as the tank test continued, the wreckage recovered from the Mediterranean was examined minutely. The location of the wreckage of Yoke Peter, south of Elba, indicates that the accident occurred about 26 minutes after takeoff from Rome, when the aircraft had reached 30,000 feet and was still climbing. In the second accident, near Naples, only a little floating wreckage of Yoke was recovered, but this and oil on the water would indicate that the accident occurred some 38 minutes after takeoff from Rome, when the aircraft would have reached the cruising height of about 35,000 feet. The wreckage of Yoke lies in 3,500 feet of water, and salvage is virtually impossible. The wreckage of Yoke Peter came back little by little, and as it did so, it was reassembled on a wooden framework. The wreckage was minutely examined, and some curious things were found. Here is one, an impression of a coin, a 1 anna piece, probably from a passenger's pocket. But before we go into details, let us jump to the answer, obtained only after sifting a great mass of evidence, and see what happened to the aircraft. This model of Yoke Peter has been specially prepared to show the structural breakup. At the top of the fuselage are 2 ADF aerial windows, similar in construction to the windows at the side of the cabin. The failures commenced at the rear ADF aerial window and then ran forward and aft along the top of the fuselage. These 2 pieces of cabin wall opened outwards and were violently projected along the wing by the force of the pressure inside the cabin. In moving out along the surface of the wing, the pieces left marks such as paint traces and scratches, which were discovered after careful examination. For example, the blue, white and yellow paint left marks right across the wing upper surface. Then a portion of the fuselage structure from the center fuselage was blown backward by the airstream and struck the port tailplane, causing the outer part to break off. The break-up of the aircraft followed very quickly. The rear fuselage came away, folding downwards about the rear spar, and at the same time the trailing edge structure was torn away. The rear fuselage fell into the sea with the open end downwards, revolving slowly as it did so. It was severely disintegrated on impact with the water. Without the rear fuselage, the aircraft was nose-heavy and turned nose-down. The resultant air loads on the wing caused the outer wings to fold downwards and under, and to separate from the centre section. At about the same time, the fuselage nose separated from the centre section at the front spar and fell tumbling downwards, finally hitting the water in a level attitude. Last of all, the centre section wing, complete with engines, turned completely over and descended in an inverted spin, landing upside down on the water. All this information came from the examination of the wreckage. The technique of examination consists of first reconstructing the pieces, then recognizing the major separations, the type and direction of failure, and the sequence of these failures. This technique of wreckage examination and deduction is a very highly skilled and complicated matter. It is something which can only be done as a result of long experience and a great deal of application. We know that the aircraft broke up before hitting the sea because varying crushing damage from the water impact shows clearly that the aircraft was in several pieces when it hit the water. For example, the centre section wing is badly crushed on its upper surface, whereas the front fuselage is badly crushed on its lower surface. Further proof of the separation of the aircraft into the main pieces is given by the fire damage, which is found only on the wing centre section. The fire damage leaves off sharply at the fractures between main pieces, indicating that the structural break-up in the air preceded the fire damage. This also shows that the break-up must have been at altitude to allow the fire to burn intensively before it was put out by the water. Thus the major separations were defined. They were then examined for their mode of failure. For example, the starboard wing failed by the outer portion bending downwards, as shown by the compression buckle in the lower skin, tension failure in the upper skin, and shear failure of the spar webs. The sequence between the major separations was given mainly by the evidence of impact marks, scratches, and paint traces. The fact that the disruption of the pressure cabin preceded the separation of both port and starboard outer wings is shown by marks on the surface of the wing made by pieces of fuselage. These marks are found on both sides of the wing separations. Another example is the piece of fuselage carpet trapped in the failure of the port tailplane. Clearly, therefore, a failure of the fuselage must have preceded the damage to the tailplane. All damage to the wreckage tells a story. The severe crushing of the engine fairings, which have been moulded to the shape of the engines by the pressure of the water on impact with the sea, shows that the engines were correctly in place.
Some of the jobs we had to do must have looked a little queer. Here we are measuring the sinking rate of components in water. We also dropped components from balloons to check their rate of fall. To assist in the reconstruction of the accident, dynamically similar models were made to determine the motion of the aircraft following various types of major structural failure. These models were launched from an airship hangar roof, and the motion recorded by high-speed cameras. To obtain true dynamic similarity with a full-scale aircraft, the model scale, density, and launching speed must be carefully adjusted. In this shot, the camera speed is adjusted to show the motion of the aircraft full scale without a portion of one wing missing. The type of scatter to be expected in the wreckage pattern was investigated by launching models from a balloon at an altitude imitating 30,000 feet. The models were designed to break up in various ways. This shot was later proved by the actual wreckage pattern to be a close representation of what actually happened to the Elba Comet after the initial failure. At an early stage of the investigation, static strength tests were made on the tailplane and elevators, and also on the fin and rudder of the Comet prototype, Victor George. The results of these tests indicated it was most unlikely that the tail unit was the cause of the accident. The stripped fuselage of Victor George was also moved into the laboratory and set up in a test rig. The wings were then attached and subjected to a strength test. This test rig, which is used for strength testing prototype aircraft, is part of the permanent testing equipment at Farnborough. The result of these tests indicated it was most unlikely that the tail or wing were responsible for the accidents. Here's another of the elaborate tests we made in our search for clues, this time on the wing fuel tanks. To take full advantage of their high flying speed, Comet aircraft are refueled at a high rate, and pressure refueling is normally used. Since the fuel tanks are an integral part of the wing structure, damage to the tanks during refueling may weaken the wing structure. A long series of tests were conducted to investigate possible malfunctioning of the system. In this test, failure of a fuel level switch has been simulated with the result of fuel issues in the blow-off vent. The wing tanks were also subjected to a cold test. A lagged fuel buzzer was used to pump fuel at approximately minus 30 degrees centigrade into the wing tanks, as laboratory tests had shown that the blow-off valve could be iced up. A refrigerating van passed air at the temperature and humidity likely to be encountered in flight through the tank venting system and over the external surface of the wing, a cold box being built over the wing for this purpose. During the test, frost formed on the fuel pipes and underside of the wing. Later examination of the elbow wreckage showed no trace of any troubles developing in the fuel system or tanks. Comet aircraft are provided with power-operated controls, and the possibility of loss of control was considered. BOAC and RAF pilots, using a flight simulator, cooperated in investigating the possibility of loss of control due to error on the part of the crew when flying through turbulent air, or the malfunctioning of the autopilot or control system. The simulator was set to represent a Comet 1, flying through a series of gusts of various magnitude and duration at 200 knots EAS at 30,000 feet. These gusts were presented to the pilot on a cathode ray tube display in the cockpit of the simulator. With powered controls, the pilot is not able to feel the loads on the aircraft as he can with smaller machines. No evidence was obtained which might explain the accidents.
To support the investigations on the ground, an operational BOAC Comet, Able Victor, was subjected to an extensive series of flight tests. Never before has an aircraft been so extensively equipped. The passenger cabin was stripped of unnecessary furnishings and fitted with recording instruments. Electrical resistance strain gauges recorded in flight the dynamic and steady loads at 60 measuring points in the aircraft. The crew were briefed before each flight. The pilots were RAF officers of our experimental flying department, and the observers were civilian officers belonging to our scientific staff. De Havilland flying personnel also took part in many of the flights. All civil aircraft are subjected to prolonged proving trials before they are introduced into service. We will range of such tests. As the work on the ground went on, extra items were added to the flight test program to confirm the results of laboratory investigations. As a safety precaution, the aircraft was flown unpressurized, the crew and observers being provided with special parachutes and using oxygen above 10,000 feet. Strain gauges at the tailplane roots and at some of the outboard positions could be combined in various ways. For instance, port and starboard gauge signals could be added to give a measure of the symmetric tailplane mode. Alternatively, the signals could be read separately when asymmetric loads were required. The aircrew and observers spent many tiring hours concentrating on their instruments. No chance of a smoke, but a peppermint helps. The maximum airspeed called for in the tests were 300 knots EAS and 0.8 Mach number, but these limits were not tested until late in the program. For the earlier flights, limits of 275 knots EAS and 0.7 Mach number were imposed. Structural vibrations were recorded and measurements concerned with the flying characteristics of the aircraft were made, together with the temperature of the engines and the cabin heating system. Throughout all the flight tests, another aircraft acted as a shepherd and followed Able Victor from takeoff to touchdown. Flight tests eventually culminated in a program of maneuvers and flights in turbulent air to check aircraft and pilot response. During these tests, Able Victor flew 70 sorties, totaling over 100 flying hours and a distance equivalent to a journey twice around the world.
We now return to the tank test, where the cycle of test was repeated continuously, apart from periods set aside for inspection, until the failure of the pressure cabin wall occurred. This happened when the equivalent total life of yoke uncle was about 2.5 times that of the Elba Comet. A small fatigue crack in the skin of the rivet near an escape hatch is considered to be the start of the failure, which developed rapidly. The damage was then repaired, and also a crack believed to be the beginning of another major failure. The tests then continued. When the equivalent total life was about 4.5 times that of the Elba Comet, a further failure occurred, a crack near a window developing rapidly, and the port side of the cabin was ripped open for a length of about 15 feet. This third failure confirmed that the structure around escape hatches and windows was vulnerable from the fatigue aspect. A series of laboratory tests were made to study fatigue stresses around a rivet hole, and specimens of aluminium alloy sheet, similar to those used in the Comet fuselage, were stressed in a fatigue testing machine 2,000 times per minute from 0 to 40,000 pounds per square inch. Under these stressing conditions, the specimen fractures in about 6 minutes. The examination of the Elba wreckage, which had proceeded simultaneously with the fatigue tests, indicated that failure started at a direction-finding aerial window in the roof of the cabin. There were 2 of these windows, and the failures originated from the rear one. On one side of the rear window, the failures run forward from a corner and pass through the front window. On the other side of the window, the failures run aft, so splitting the fuselage along the top center line. Under the action of the internal pressure, the 2 halves opened outwards, broke away, and were projected violently along the wings. There's a strong similarity between the failures in the wreckage and in the fatigue tank. When seen side by side, these failures provide a most striking demonstration of circumstantial evidence. All the structure in the region of the ADF aerial windows was microscopically examined, and strength test specimens were taken from the material. In one corner of the rear window, signs of fatigue were found. This direct evidence of fatigue, and the close similarity with the failures in the pressure cabin fatigue test, gives convincing evidence that the disruption of the pressure cabin was brought about by fatigue.
Members of the Comet Court of Inquiry visited Farnborough during the sitting of the court to see at first hand how the accident investigation was carried out. The conclusion of this investigation into the Comet accidents enables us to face the future of British civil aviation with the confidence that the lessons learnt will be put to good use. The full-scale test techniques and equipments evolved to carry out these tests have given us valuable experience of test methods which will help to ensure that future Comets and other British high-performance passenger aircraft will fly with safety and speed on the air routes of the future.